Okay, so heat transfer. Heat transfer. Heat transfer is symbolized by the symbol Q. So what's the definition of heat transfer? So heat transfer is the transfer of energy between systems due to a temperature difference. Due to a temperature difference. So let's say I have two bars. Kind of like on the first day of lecture, we talked about, introduced the concept of heat transfer involving two bars that were in contact. Remember that from the first lecture? So we have bar A and we have bar B. And let's say TA is greater than TB. So this is the hot bar, and this is the cold bar, okay? So as a result of the temperature difference here, heat is going to be transferred from the hot to the cold bar. So we have heat transfer. And as far as A is concerned, so system A is the hot bar. As far as system A is concerned, QA is negative. So we have HT, heat transfer from A. So energy is flowing from A to B because A is hot, okay? So QA, heat transfer to system A is negative. Heat transfer is positive when it's to the system and negative when it's from the system, okay? Heat transfer is positive when it's to the system and negative from the system. Likewise, QB, heat transfer to system B, to system B is going to be positive. Why? Because we have heat transfer to system B. Okay? So Q is positive to system, negative from system. Okay, the opposite of work. Remember boundary work? That was positive when energy left the system in the form of boundary work, or the system did work. Where heat transfer is positive when you're doing or adding heat to the system. So Q is positive when you're adding heat to the system, and is negative when heat or energy is leaving the system or you're extracting heat from the system. What about some notation here? What about some bases? What about some bases here? Basis. So we have basis, we have expression, and then we'll talk about SI units. And English units for heat transfer, okay? Basis, overall process. Overall process. So that means Q from state 1 to state 2. That would be a way to symbolize heat transfer for some overall process. So we have a system which moves from state 1 to state 2 because we are adding a certain amount of heat, Q1 to 2, making the system hotter, increasing its volume, doing something, okay? An SI unit of energy, of heat transfer is energy, same units as energy. So we would have joules. In English units, we would have the BTU. BTU. All right. What about for a differential process? Differential process. That would be a little bit of heat transfer. Notice the lowercase delta there. Q is a path function, not a point function. So instead of writing dq, you write delta q, the Greek letter lowercase delta q, because heat is a path function. Units are energy. Okay? It's just a small process, a differential process. There's also the rate-based in other words, the rate in which heat transfer is done. That would be represented by Q dot, which is the little bit of heat transfer over a small amount or infinitesimal amount of time. So Q dot is equal to delta Q divided by dt. Time is a point function, so I put a d there. Heat is a path function, so I put a delta there. The units will be watts, which is a joule per second. So joule per second or a watt. Or a watt, joule per second or a watt. And then we have horsepower for the English unit. You can also write this heat transfer per unit mass. So there's also, I don't know, overall per unit mass. I could do that. That would be Q divided by the mass of the system, or lowercase q. Lowercase q. Okay? You can write 1 to 2 on there if you want. And that, of course, would have units of joule per kilogram and SI and BTU per slug or something. Pound mass. Okay? If I knew the mass of the system, then I could divide the heat transfer by the mass and I'll get heat transfer per unit mass. Sometimes that's an interesting way to look at heat transfer per unit mass. Okay? So these are the various bases or ways that we can express heat transfer along with their units and the symbols used to represent them. By the way, the same thing can be said for work. I didn't draw this table for work, but you could replace everything in here, every Q in here with a W. Work for an overall process, W1 to 2. Differential work, del W. Rate work over a certain work on a rate basis. So that would be W dot, del W over dt. And then we'd have lowercase w, which would be the work over the process divided by the mass of the system. So I can rewrite this, make this entire chart by substituting work for Q. Substituting work for Q. Okay, so we can do the same thing with work. All right, so heat transfer. Heat transfer is the transfer of energy between systems due to a temperature difference. Heat naturally flows from hot systems to cold systems. Heat transfer is positive when energy is being added to the system, and is negative when energy is flowing out or being extracted from the system. And then we have the various bases for heat transfer or work. You could do this whole table with work as well. All right? Okay, let's move on to the next topic here. Let's actually start getting into more detail on heat here. This has just been a bunch of qualitative stuff. Just been a bunch of qualitative stuff. Now, why do we add heat to a system? Well, one of the reasons we add heat to a system, probably the most relevant reason we add heat to a system, as far as everyday lives are concerned, is to increase the temperature. You add heat to a pot of water, and you raise it up to the boiling temperature, and you make your tea, or your coffee, or you boil your potatoes. Okay, so that's one of the most fundamental applications of heat transfer, to raise the temperature of a substance. Let's look at adding heat to a system for two different paths or processes. And the topic here we're going to be leading into is called specific heats. Specific heats. So let's say I have a container here, a piston cylinder device, in fact. And I have some sort of mass in here, some sort of material with a certain mass. And it starts off with a temperature T1. So this is state 1. And now I'm going to add heat. Q 1 to 2. Q 1 to 2. I'm going to add some heat. In fact, I'm going to add a very small amount of heat, a differential amount of heat, very small amount of heat. Del Q. Let's add a little bit of heat. In fact, I'm going to get rid of this 1 to 2 right here. I'm just going to leave del Q, just for notations purposes. So we're going to add a little bit of heat. And so presumably the system expands ever so slightly. So the piston is now moved up because the system has expanded a little bit. And now I'm at a temperature T2. So this is my state 2. All right? And by the way, what's state 2? What's temperature at state 2? The temperature at state 2 is equal to the temperature at state 1 plus the differential change in temperature. So T2 is T1 plus a differential, dt, differential change in temperature. So I add a differential amount of heat, infinitesimal amount of heat, del Q, and it warms up the system by an amount dt. Small heat transfer results in a small temperature rise. Now, let's define specific heat at constant pressure. I'm in a piston cylinder device here. This is a piston cylinder device, so I'm going to make this an isobaric process. What's isobaric mean? Constant pressure. baric, iso, constant pressure. I'm going to define the specific heat at constant pressure. Cp equals specific heat at constant pressure. Specific heat at constant pressure, Cp. How's it mathematically defined? Take the amount of heat I've added, del Q, divide it by the mass of my system, M, and the temperature change, dT. Cp is equal to del Q over mdT for a constant pressure process. Constant pressure process, del Q over mdT. If you like, specific heat is the amount of heat required to raise the temperature of the system by 1 degree per unit mass. The amount of heat required to raise the temperature of the system by 1 degree per unit mass. Cp equals del Q over m dt for a constant pressure process. Put a box around it. That is the definition of specific heat, constant pressure. What's the units of this? What are the units of this? Well, in metric, well, in anything, I guess energy per unit mass per degree. Hence, Cp is the energy required per unit mass per degree for a system. Okay, so that's Cp. There is another specific heat. Remember, heat is path dependent. So specific heat will be different depending on the path. That quantity, del Q over mdT, will be different depending on the path taken. For a constant pressure process, we let Cp equal to del Q over mdT for a constant pressure process. What about if instead we have a rigid container? A rigid container. So we have a certain amount of mass in here and we have a T1. And this is a rigid container, so volume is constant, a rigid container. So I add heat to my substance in this rigid container, Q. It's a differential process, so I'm adding del Q, and I end up at state 2 with a temperature T2 is equal to T1 plus dt. Okay, same thing as before, except we have a constant volume process. Isochoric process. What's isochoric? Constant volume. Constant volume. So we have a new specific heat defined because the path is now different. Instead of traveling an isobaric process, we're now transversing an isochoric process. CV, constant volume, not constant pressure. CV is equal to del Q over m dt for a constant volume process. Specific heat at constant volume. Specific heat at constant volume. At constant volume. So put a box around this. You need to know the definition of specific heat. You need to know the definition of specific heat, both for constant volume and constant pressure. So you need to know this. Units for this are energy per unit mass per degree, or if you like, the amount of energy required to heat up 1 kilogram of the substance, 1 degree for a constant volume process. That's what CD, the number, represents. Okay? All right. Let's talk for a minute here about, oops. There we go. Let's talk for a minute here about how you calculate specific heats, and then we'll move on and do an example. So how do you calculate specific heats? In fact, I'm going to write them right over here. So specific heat at constant pressure is the little bit of heat added per unit mass per degree change. And then we have, and this is for constant pressure. And then we have CV, which is the little bit of heat added per unit mass per degree change for volume equals constant. Okay, constant volume. Let's put a little box around these. These are going to be important. We're going to be using them. Hell, we're going to be using them throughout the semester. Now, the first thing I want to point out is that CP is typically greater than CV, for almost all applications. So why would specific heat at constant pressure be greater than specific heat at constant volume? Let's put the picture up again. Let's put the pictures up again. We have our isobaric process. So heat is being added, and if it's isobaric, that means that the piston has moved upwards. Here's our system. So we're adding heat. Let's say we're going from state 1 to state 2, and I have a temperature T1 and I have a temperature T2. Okay? So that's the constant pressure process. And then we have the constant volume process, which involves a rigid container. So we're going from state 1 to state 2, and we're adding heat Q1 to 2. And I have a temperature T2 and a T1. So why might these temperature differences, T1 and T2, why might the heat transfers be different? Why might the heat transfers be different, required to affect the same change in temperature for a constant pressure versus a constant volume process? If I'm going to raise the temperature of both these systems by 1 degree, and they both have the same mass, let's say, why do I have to add more heat for the constant pressure versus the constant volume process? Well, the reason is because here in the constant pressure process, boundary work is being done. The system is expanding. So some of the heat is being used not only to heat up the system to produce a temperature change, but to expand the system. We're doing boundary work for the isobaric process, whereas the isoporic process has no boundary work. No work bound. And in this case, work bound is greater than 0. Okay? So that implies that Cp, the amount of heat to raise the temperature of the material, let's say by 1 degree, is greater for a constant pressure process than for a constant volume process. So this is due to presence of boundary work for isobaric process, due to presence of boundary work for the isobaric process. All right? Another thing to notice about specific heat. Let me tell you a few more odds and ends about specific heat. And we're going to be coming back to this stuff later, but I'm just kind of trying to whet your appetite. So if you see this, it'll jog your memory when you see it the second time. You'll be seeing some of this information the first time now, and I will be proving it to you later on. So another little fact about specific heat. Cp is equal to Cv. Specific heat at constant pressure and specific heat at constant volume are equal to each other for solids and liquids. Cp and Cv are equal to each other for solids and liquids. Why might that be the case, given what we just discussed? Is a solid compressible? Does the volume change in a solid when we raise or lower its temperature? Does it change a lot? Let's say nearly as much as a gas. And the answer is no. Solids are essentially incompressible. They do expand a little bit, very small amount when you heat them up, but nothing compared to a gas. Nothing compared to a gas. Same thing for a liquid. Liquids do expand or contract slightly with temperature, but nothing compared to a gas. So specific heat at constant volume and specific heat at constant pressure are approximately equal to each other for solids and liquids. They're exactly equal to each other for incompressible substances. Okay? No boundary work possible for incompressibles. A gas is not incompressible. Liquids and solids are approximately incompressible. If you want to be absolutely strict here, just put approximately equal if it makes you feel a little bit better. Okay, so Cp and Cv are the same for liquids and solids. So that's another fact. Ideal gas. Let's say we have an ideal gas. Ideal gases. Let's look at what we can say about, what we will be saying about Cp and Cv for ideal gases. In general, specific heats are a function of two things, temperature and pressure. These specific heats, the numbers that you look up in tables for particular substances, they tend to vary with temperature and pressure. In fact, let me state that right now. Note, Cp is a function typically of temperature and some other stuff. Typically a temperature and a pressure, a temperature and a volume, something. So Cv is a function of temperature and some other stuff. a temperature and a pressure, a temperature and a volume. So there are tables for specific heats, and they're typically functions of temperature and or pressure, okay? But for ideal gases, specific heats are a function of temperature alone. Cp is a function of temperature alone, and Cv is a function of temperature alone. Why is that? Because we already have an expression that relates pressure, temperature, and volume, the ideal gas law. So in theory, we can solve for one or the other and reduce a two-variable dependence into a single variable dependence because we have the ideal gas law. So in general specific heat, Cp and Cv for ideal gas behavior is a function of temperature alone. And these Cp's and Cv's are tabulated, as you will see soon. All right? Okay, so let's do an example here. Let's go through and do an example.